So we're going to talk about parametric curves. These are puzzles, and you're going to have to do them yourself. But I'm going to give you some clues. So this is going to apply to more like question 1, but you're going to have to, again, do them all yourself. So I'm going to just make up something. I'm going to make up 2 plots and then say what would happen if these were parametric curves. How would you figure out what the parametric curve was doing? So I'm just going to do something like horizontal line at, let's say, 3, and then this is x as a function of t. This maybe goes to 2, and then maybe I'm going to come down to 4. So I'm just going to make something up. And I'm going to go up, and I'm going to make it a little more complicated. I'm going to let this be at 3 and 4. I'm going to go up to a height of 10, I guess. And this is going to be y of t. Well, how do I then figure out what the parametric curve looks like in the xy plane? Okay, so I have 2 parametric curves, and I want to combine them. All right, so I'm going to make this set of axes down here. Now this one is special because if your x of t is a line and your y of t is a line, then your resulting function still has to be a line in the xy plane. So that's why we're starting with this example. So what I'm going to do is I'm going to make myself a little table, t, x, and y, and I'm going to find any point where I think it might turn around, and I'm going to plot them over here. So at t equals 0, I'm interested. At t equals 2, about 1, 2, 3, 4. Hopefully this should get us everything we need, and we'll figure out the direction of the particle's motion. Okay, so at 0, I have x is 3 and y is 0, and then at 4 it's at 0, 0. So at least we know that. Now what's happening at t equals 2, x is 3, and then it goes down to 0. So what are we doing between 0 and 2? X just stays 3, so x of 1 is 3. What about x of 3? Well, it's like 1.5, so 1.5. So at least we know what x is doing. So what is y doing? Well, y just takes 3 units to get all the way up to 10. So it's 1/3 of the way, so 3 1/3, and then like 6 2/3, and then it's going to get up to 10. Okay, so now that we have an idea of where this particle is, and again, we're lucky because in this case, when we combine lines like this, as long as we make sure anywhere there's a change like that, we've accommodated all those considerations. So now we can just connect the dots. All right, so we'll start at 3, 0, so maybe this is 3, 0. That's where it starts at time 0. And then x stays at 3, but y is going to increase to 3.5. So the first piece, the first thing it does is it goes up to about 3.3. So this is this path here. I'm going to change color so that we can see what's happening in the next link. Okay, so and now x is still going to stay on 3, but we're going to go up again. So let me just move these guys around so I have more room to draw. Sorry about this. All right, now I'm going to just keep drawing this guy up another about the same length, and this is going to be at about 6.7 roughly. Okay, now I'm going to keep going up the same amount for y. But now the x is doing something different. The x decided to start coming halfway back again. Okay, so now I'm going to like use orange. I'm having trouble seeing my pen for some reason. I'm going to move to 1/2 and 10. So this is about 10. I'm going to do this link. There we go. And what happens at the end, I have to come back home. So I have to spend the rest of this time coming back to the origin, and this is a little harder to draw. I'm going to use a different tool for this. It's a little easier. Okay. All right, so that's what this looks like. I think I meant to draw this bracket. Okay, so hopefully then you're going to use the same process for question 1, and then you should be able to answer everything that's going on in 1 A, B, C, D, E using that technique. Okay, so question 2 requires that you understand something about circles, and you're going to have to solve this problem. You actually already have enough to solve 2B based on what happened in the previous piece of the video for question 1. So you can apply that. So but for question 2A, you need to know something about circles and how they relate to trig functions. Okay, so let me draw some first. Okay, so let's say we have x of t is sine of t and y of t is cosine of t. How will we put that together in combining that into a single curve? All right, now we happen to know that sine squared plus cosine squared equals 1, and that's helpful because we know that all the points that we're going to plot have to lie on this circle. So they have to lie on the unit circle, but the question is, what is the actual path of the points? And even if you made x of t is cosine of t and y of t is sine of t, you flip those guys around, it doesn't matter. In this regard, you're still going to trace out the unit circle because obviously sine squared plus cosine squared is 1. So you are confined to be on this circle. There's nowhere else you could possibly be. So you have to be on that circle. So that's half the battle. And the other thing you know that it's cyclic. So wherever you are at t, so x of 0 has to equal x of 2 pi, and same thing for y, or x of any time is equal to x of that time plus 2 pi. So you know it's periodic, and the same thing happens in the y. So the great thing is you just have to figure out what happens between 0 and 2 pi, and then you know everything. All right, so where is t equals 0? So t equals 0 starts when x is at 0. All right, so if x is 0, then it's one of these 2 points, up or down, and y is 1. So this must be it. It must be here. This is t equals 0. Now, how do you know which way it's going? Lots of ways to figure that out. But let's do something else that's more obvious first. Let's just go and say this must be t equals pi, and we still have no idea which direction it's moving, right? So clearly, we're either going to go this way towards -1 or this way towards +1. One of those two has to be the where, for example, where t equals, let's see, pi over 2. So at t equals pi over 2, let's investigate. At t equals pi over 2, x is indeed 1. So this must be t equals pi over 2, so that means we're moving in this direction. Okay, so we figured that out. Now let's just double check and make sure everything matches what we just said. We're going to look at this and say what happens in quadrant 1. We're traveling this way. X is going from 0 to 1. Is x going from 0 to 1 for the first quarter of this path? Yes, it is. So as we're traveling along, that's consistent. And for y, is it going from 1 down to 0? Yes, y is going from 1 down to 0. Beautiful. Okay, that's great. Now, just for fun, let me try flipping these guys around. Let this be y and let this be x. It's going to change all these time, and it might flip the direction. So let's just try this. But again, we're confined to be on the unit circle. So what happens now at x when t equals 0, that means at t equals 0, we have an x and a y point equals t of 0 means t at 0 means cosine of 0 is 1 and sine of 0 is 0. So this must be t equals 0. And obviously this must be halfway around the circle. T is going to be pi. So are we going clockwise or counterclockwise? So let's go ahead and test this. At t equals pi over 2, you're going to get sine and cosine are actually going to be 0 and 1. All right, so this is going to be t is pi over 2. So we've actually we're moving in the other direction. Okay, so we're moving counterclockwise, or otherwise a positive direction. So by changing whether you put sine or cosine on the x or the y, you can flip whether the thing's going clockwise or counterclockwise. You can also build ovals very easily by this process. Let's say we just wanted to make this 2 instead of 1. We can easily just stretch out the x coordinate like so. And I'm just going to do this visually for you to make you realize that, okay, you can just stretch this and it doesn't matter. Okay. And that information should be enough. Let me just look at the worksheet for a second. Yeah, I've given you enough clues to get you through number 2. Okay, now we're going to go on to question 3. These are puzzles that I want you to play with, but I'm just going to tell you about the structure of the problem. So you have cosine of f of t, whatever f of t is, and then y is equal to sine of f of t, and we could easily flip the sine and cosine. But you still have this property, x squared plus y squared is going to be cosine squared of something, whatever it is, plus sine squared of something, whatever it is, has to be 1. So you're still going to be living on the unit circle, just like we were in my last example for question 2. So you're going to be stuck on the unit circle. You cannot get off the unit circle, but you can figure out where on the unit circle you're starting and whether you're going clockwise or counterclockwise. And some of these problems have you go like rocking back and forth, like kind of like that. All right, so you're confined to live on the unit circle, but there's still plenty of flexibility for how this thing travels. Okay, question 4 is more just crunch it out. This is not really meant to be puzzly. This is just straightforward. So you have some kind of x of t is some kind of polynomial, and y of t is another, polynomial, whatever. It doesn't have to be a polynomial. It just means it's something that you can easily take the derivative of. And then at t equals 1 or whatever, find the tangent line. Okay? And so what do you need to find a tangent line? You need a slope and you need a point. That's all you need to find a line. To find the point, all you have to do is plug in x is 1, y is 1, and then it gives you a point. Okay, so the point is just literally x of 1, y of 1. So I'm not going to go over how to do that. Now the question is, how do you find the slope? And so what you want to do is the y dot over x dot is going to give you the slope. You just calculate whatever y prime is, y prime of t, which is, I also call it y dot, and you calculate x prime of t is equal to x dot. Then think about what's happening in microscopic scale. Okay, so this piece is going to be dx dt, and this is dy dt, and for a specific time slice you get yourself a triangle. So what happens when you say dx over dt is one piece you have, and you have dy over dt? Wouldn't it be great if we could just divide these? And in fact we can, because it really, when we write dx dt and dy dt, we're really thinking in terms of little tiny pieces of time. And as long as the time piece for which you allow the particle to travel in the x direction is the same time as you're allowing it to travel in the y direction, so that time piece disappears, and you're really left with what is just dx and what is just dy. So if you think about what this means, it makes perfect sense, and that's how you extract the slope out of this mess. And then you're just back to middle school math, where you've got a point and a slope, and you just create a line. And that's all there is to that one. Just for people who have had it, this is an aside, if you have some function, let's just say x of t could be 3t plus 1, y of t is equal to 4t minus 1. There is a notation that we have not yet introduced, but we could, if we wanted to, write it this way. So if for those of you who have done it before, that's totally fine. And in that case, well, a tangent line of a line is just a line, but the point is there is a way of writing the line where you would write the line is, you would put some expressions here and put the t, and then you would put some kind of starting point which is equivalent to your y-intercept, but it could be anywhere. If you're used to using this notation, I'm fine with that, but for this one exercise, I want you to just use the typical middle school math way of writing stuff, because that's what you're going to need to feed into your quiz. Okay, so for speed, if you have a parametric representation of your curve, then you're going to look for, again, you're going to look for x dot and y dot, and you're going to look for the total speed is going to be x dot squared plus y dot squared, and then you're going to take the square root. So you're going to have this expression. It's very familiar to you at this point, right? You're gonna know that that's your speed. Okay, so your question is a little bit harder than that. So it says find the speed of motion for a particle at what time does the particle stop. And the reason why this I think is a little bit tricky, because you don't actually have to figure out the speed of the particle in order to figure out when it stops. So what I'm going to encourage you instead to do, I want you to do both, but I want you to think about this conceptually. You have some kind of curve for x of t, and you have some kind of curve for y of t. And wherever x of t has a max or min is a potential stopping point. And wherever y of t has a max or min is a potential stopping point. It has to, the curve will stop moving if both the x and the y are paused at the same time. So like if I find out that this is at t equals 17 and this guy is at t equals 17, then the particle has to stop, because it's neither moving in the x direction nor is it moving in the y direction. So if my particle, let's say my particle is moving like this and then like goes up and then comes back on the same path, for example. It has to come back on the same path or else it means it didn't stop. I guess you could have a cusp like that for a second, but in this case, in your exercise, it's going to be stuck on an oval anyway. So it's going to go up and it's going to turn around at a certain point. And if you think about that, how that looks, if you're going up to a point and then turning around, what does that look like in the x direction? Well, in the x direction, you go forward and then back. So what would that look like? If your motion is going up and back, so you're going to start here at 0 and you're going to turn around at like time 2. Then what is the x of t going to look like? Well, it's going to increase and then it's going to come back down, right? So it's going to hit a max and then it's going to go back down. Well, what is the y going to look like? It's going to do something very similar. It's going to hit a max and come back down. So every time a particle turns around or stops, that means both of the parametric curves have to have a max or a min, an extreme value. So that's your trick for figuring that question out. Okay, and that's all the hints you need. I will see you in class. Have fun.